Okay, so what we do today is we'll just first recap what we have done yesterday and then proceed. Okay, so yesterday what we were trying to do is we were trying to write the equation for first derivative and second derivative and mixed derivative, right, in terms of variables, right, in a form of algebraic equation. So we were trying to convert a derivative into an algebraic equation, and that would introduce some error which is called truncation error. What we had done is, for a first order derivative, for the first derivative we have found a forward difference which was represented by this line. Okay, so the derivative is your derivative at this point is del y by del x or del u by del x. Okay, and this was the forward difference, and they were almost equal but not exactly equal. If we go for backward difference, this was the slope which we get from the equation, and this is the actual slope, and they are nearly equal. And we also talked about that if we reduce this distance delta x in the backward direction as well as in the forward direction, what will happen? The calculation of derivative by algebraic equation will approach to the actual derivative. This is what will happen. And then we said there is other option is that you can combine backward and forward formulation, and we can make a central difference formulation, and in that case we will find that this will be the derivative as per the algebraic equation. So if we talk about the central difference, then we take these 2 points A and C, and with those points what do we get? We calculate a derivative using a algebraic equation and compare with the differential equation, and they are nearly equal. Again, even this you can't say this is also absolutely same. They are not exactly equal. There is some error, and the reason for error is that we are leaving out the truncation error. The certain terms of the higher order we are leaving out, which leads to some error. We found that the order of error in the forward difference is 1. Similarly, in the backward difference method, the order of error is 1, but in the central difference the order of error is 2, which means that we are improving upon that. Okay, our central difference is 1 order more accurate than your first order. Okay, now then we talked about the second derivative, and we got this as the formulation for the second derivative, del square u by del x square. Again we found that this the order of error is 2 here, truncation error. Okay, this is also an algebraic equation based on central difference. So we are taking 1 point on the right, 1 point on the left, and of course the central point also matters in this case. Okay, so this is what we have done. Then we moved on to this mixed derivative. We talked about mixed derivative, and in case of mixed derivative again we wrote an equation, and the equation was of this form. Okay, and when we talk about truncation error, there are 2 truncation error. One is in the form of delta y square, and 1 is in terms of delta x square. Now this delta y square is being multiplied by a difference in third derivative of u with respect to y, and this would actually lead to a smaller number. So both, I have a hunch feeling that both for this x and y this will be second order, while here it is not second order, this is first order. Del y square is second order, you are dividing by delta x, so this is one order. So this actually, this whole term would mean that your error is of first order. Here it means it is of second order. So this formulation is telling you that the error is in terms of x this is second order, and in terms of y we are still not sure. And from this term, if we look at this term only, it is seems to be first order. But then we are multiplying by this number, which is a difference of derivative. So this will actually reduce the increase the order by 1. So probably it will go to del y cube by del x. Okay, but we leave at that because that would involve a lot of mathematics. So we leave at that point. So then we found that when we are talking about derivative, the mixed derivative at this point, these are the 4 points which become relevant. Okay, while the derivative is actually depends on the function at that point. Whenever you are talking about del u by del x or del u by del y or del square u by del x square, del square u by del y square, these are the derivatives. There is another del square u by del y del x. These are the 5 derivatives. 3 of them are second derivative, 2 are first derivative. On what does they depend? They depend on the function and the point. So basically they are a function of f x comma y and xy. So at whatever point you are finding the derivative, you must know that point and the function at that point. While when you are talking about these, they are in terms of algebraic equation. Okay, so when you are talking about, let us say, del u by del x, right? So you are talking in terms of ui plus 1 comma ui, or you are talking about in terms of ui minus 1 comma ui, or you are talking in terms of ui plus 1 comma ui minus 1, right? And when you are talking about del square u by del x square, you are actually talking about ui comma ui plus 1 comma ui minus 1. And when you are talking about del square u by del y del x, you are actually talking about ui plus 1 comma j, ui minus 1 comma j, ui comma j plus 1 and ui comma j minus 1. So 4 points are here. In all this equation, what you are finding that you are talking in terms of adjacent points. More than 1 points are there, and they are the adjacent points. So what you have done is, from the function and the point, you have moved to surrounding point, neighboring points, right? This is the reason for error also, and this is the reason for, this is the approach which helps you solve it, because you are converting differential equation into algebraic terms, okay, equation. So this is what is happening. Now, when yesterday I was telling you that we actually are talking about the points which are inside the domain. which means there are left point at the left and the right and the top and the bottom, etc., etc. Once you come at the boundary, on one side there are no points. The points are only on the other side. Now, if you take this case, okay, you can write here, I can write del u by del x, so del y, as I can say u2 minus u1 by delta y, right? u2 is this, u1 is this, and u3 is this. You can write. So you are able to write derivative at this point in terms of this point and this point, and both of them exist. But that is a forward difference, first order. Now, if you want to move on to the second order, what do? Second order, what we have done is the central difference. That means we needed a point here, but we don't have a point on the back side, outside the domain. There is an option available to us, okay? And again, it is just to show you, this is not the only one. Let me tell you, this is not the only one method. I am just picking up some isolated cases so that you know what is happening. Okay. So now this first order backward difference for the first derivative is not feasible at the boundary point. So the backward difference is not possible. The second thing, again, the second order central difference of the first derivative is not feasible at boundary point y1 equal to 0. Again, central difference is not possible. So out of 3, only 1 is possible, and that too is of truncation error of order 1. Okay. Now fortunately there is an option available to us that we can have second order forward difference for the first derivative using polynomial. Now we can write an equation using 2 forward points, which will be truncation error will be of the order of 2. So what happens is you can increase the number of points. So you are able to trace the function more accurately. So as you take more and more number of points, your calculation becomes more accurate. This is what truncation error keeps on going down, and the order of truncation error keeps on going up. So this is possible, and how do we do it? So the question before us is whether we can write an equation for del u by del y at point 1 with truncation order of 2. So this is not the only solution. I told you that this is one of a sample case. There could be different methods also, but that would mean and actually unnecessarily will be lost in same type of things without getting the whole idea about CFD. So because if we do go too much here, we will lose somewhere else. So it's better that we take it as a sample case. So what we do, the solution is that we assume a function where u is equal to a plus by plus cy square. So we are assuming a function where a, b, c are coefficients or constants. Okay. Now we have to find these coefficients. What are these coefficients? Because unless until these coefficients are known, we don't know what the equation is. We know that y1 is equal to 0. You put in the above equation, you will get u1 equal to a. Again, when I am solving this, don't fall into the mathematical part of it. Just focus on the conceptual part what we are doing. Mathematics is all there. You can sit simple mathematics, you can follow it, and with some effort you can do it yourself. Okay. Mathematics mein what is the problem? The only problem is there might be some hidden technique which you do not know. There's a difference between mathematics and physics. In physics you have to understand what is happening. In mathematics, once you understand the question, that is not enough. You have to solve it. And solving is a question of technique. You might get some tricks are there. So we are not here to learn the tricks, how to do it. They are there, you can see those tricks and you can get it. What are the steps to be followed? You can see that. At least we should understand what is happening. Okay. So what we do, we are able to find A. A is equal to U1. Then if we put Yt is equal to delta Y, you get this equation. U2 will be equal to B delta Y plus C delta Y square. U2 is the value of the function at point 2. This is the value of the function at point 1. Okay. Similarly, Y3 equal to twice delta Y. Your U3 will be equal to A plus 2B delta Y plus 4C delta Y square. Now you can use all these equations. There are 3 equations and 3 unknowns. U1, U2, U3 are known. They are not unknowns. Unknowns are A, B and C. Delta Y is also known. You have already made the size of the grid. Delta Y is known to you. Now this gives you these 3 equations. A is equal to U1, B is equal to this one and C is equal to this one. Okay. So what do we finally get? Okay. Now we will talk about first derivative. So this equation which we were talking about, we can know this equation now. A, B and C are known in terms of U1, U2, right? So you can fill here and you'll get it. Or U3 also, right? U1, U2, U3. You fill it, you'll get it. Okay. Now we talk about first derivative. First derivative will be equal to B plus 2C delta Y. Now at point Y equal to 0, del U B is equal to this. Del U1, derivative at 1.1 is equal to B. Okay. So you put this, what do you get? Okay. So you put the value of B here and you get this. So now derivative you have got in terms of U1, U2, U3. Got it? Same thing we were doing. There we were writing derivative in terms of Ui plus 1, Ui minus 1, right? Or both Ui plus 1 and Ui minus 1. Here we are doing 3 points U1, U2, U3. Something like that. Ui plus 1, Ui plus 2. Right? Because we cannot go on the back side, we are going on the forward side. And that is why the equation is also changed. Right? Had it been on the back side, it would have been U2, you can say, there would be 3 points now. Now U0, U1 and U2. So this will become U2 minus U0 by twice delta Y. यही तो बनेगा सेंट्रल डिफरेंस. Forward minus backward divided by twice delta Y. But here you find it's something else. Minus 3U1 plus 4U2 U3 divided this. This is equal to B. That you know from the equation. And B you have calculated already. So this is. Now, so you, okay, I have already written here. So if you had done this is the forward difference. Forward difference. And here you see there are 3. They are also forward difference, but there are 3 points, 1, 2 and 3. Here there are only 2 points, 1 and 2. Okay, and this is order of error is here 1. Now we have to see what will be the order of here. Okay, we are not using here, we don't know what are the other terms. We have gone in a different way here, right? So what do we do now? We try to find out, okay, finding the second derivative. So there is one more thing, second derivative. How do we find the second derivative? If you find the second derivative, this is the equation, okay, and this is the second derivative. Now remember one more thing, you do not know the function, this function u as a function of y, this you don't know. You don't know. What you are assuming is u is equal to a plus by plus cy square. So these two functions are not equivalent. What is the real function? You don't know. You are assuming this. Therefore, there is an error as compared to the real function. And we are trying to find out that. Now, if you find the second derivative, it is equal to 2c, and 2c already you know. 2c is equal to c is equal to this. So the second derivative. So second derivative also you can find out. These equations are accurate. But the problem is your equation is approximate. You have not made any assumption while doing the assumption you made is that your function is u is equal to a plus by plus cy square. This is the error you have introduced. What is the real function? It is sine, cos, log, or what is it? Is a polynomial of first order, second order, third order, fourth order, nth order. You don't know. You have assumed for your convenience that the order is 2 or second order polynomial there. So what you are leaving out? You are leaving out the terms of higher order there. So now we have to find out what is the order of truncation error. So how do we do it? If we solve this, this is from Taylor series, and if you write the equation in this form, you get this, and from here if you truncate here at this point, truncation error is of order equal to del y square. Order is 2. Right? Now, the same thing we have done. This is the. Now, what we will do is, now we will show that the formulation we have written that is similar to this. And because it is similar to this, the order of error in both of them are same. Okay, so how do we do it? Our equation is this: u is equal to a plus by plus c square. Now we know u2 is equal to this much, okay, and a is equal to u1, we already know. This derivative we know, this we know, we have already done them. Okay, so what we do, and substituting a, b, c respectively, what do we get is this. Okay, u2 minus okay, this you are substituting. This is the equation which you got from Taylor series, truncated series. Okay, now from there you get del u1 is equal to this much. Okay, now let's rewrite this equation obtained from Taylor series again. Okay, so what he has done is, what we have done is, you have equation u is equal to a plus by c delta y square, right? So u2 will be equal to what? A plus b delta y plus c delta y square. Correct? It is actually a y square, and this is the equation because u2 is y equal to delta y. Okay, now what has done, we have put the value of a, that is equal to u1, and this is, we have put the value of b here, del u by del y, and the value of c here is this, c is equal to half of this. Okay, so this equation we have got from, not from Taylor series, but from this equation. Okay, so this is, you do the jugglery, you get this equation. From here you get this equation. Now you compare this with Taylor series. This term is same, this term is same, right? This term is what? Same. Right? What is different? This is the order of truncation error. So that means in the above equation also the error is 2. Right? So this is what we have done.
Equation
u3 is at y equal to twice delta y. You have y equal to 0, then first point, second point is at y equal to delta y, and the third point is at y equal to twice delta y. We can go back. u2 is this, u3 is this. So this is your derivative, right, which we have got already. Thus we can, let's compare this equation this. So we have found that if we compare this, the truncation error is order of 2. Remember here, in case of Taylor series, we had let certain terms, and the error is because of the terms we left, higher order terms. Here in this formulation, the error is because you have assumed a function which may not be the real function. So the error is coming because of that, right? So, and the order of error in both the cases is same.
लेकिन जब अगर हमने एज्यूम किया है कि हमारा कोई भी फंक्शन जैसे सेकंड ऑर्डर में फंक्शन ले लिया है जो एक्चुअल रियली रिप्रेजेंट नहीं कर रहा, तो हमारा एरर रैंडम हो जाएगा
नहीं, ए बी एंड सी यू आर फाइंडिंग आउट ना,
लेकिन
so
वो एक्चुअली रिप्रेजेंट नहीं कर रहा तो हम किस basis
It is approximately representing it, na? Because A, B, C depends upon the U1, U2 and U3. They are trying to, is something like this. Let me say, you have made a valid point, and we can suppose this is your U and this is X. Okay. Now, my equation is, let us say, it is going like this. This is my curve. Right? Now, what I have done is, I have taken 3 points, right? And tried to draw a curve with this. So what will happen? 3 points give you a quadratic equation. So this is not a quadratic equation, which is the function. So basically you are actually drawing equation like this. What you have assumed is this. What is reality is this. But because you are doing it in a narrow area, you will be, I have a curve like this. And I want to represent by is a quadratic curve. So maybe I will be actually drawing like this. Okay? Or in a way, because I am taking these 3 points, maybe if the curve is like this, so I might be actually going here. This is the 3 points. Okay? And using these 3 points, the curve I may be drawing is, it will go like this. This is what it is introducing the error. Okay? So is it clear now? Okay. Now you know and you can guess that if you want to improve the truncation error, you can take more points. More points, you can trace the curve to a better accuracy. So more the accuracy you want, you keep on adding more and more points. But once you add more and more points, that means for each equation you are considering more points, and that becomes a slightly more complex equation. We'll come to that, what is the problem with that. So there is a solution available to you. Either you reduce the size of the grid. If you reduce the size of the grid, again you are more accurate in that region. Or you take, if your grid size is bigger, you take more number of points, and then also you are accurate. But you will never be 100% accurate, because the equation may be 10 order, 20 order type of equation, right? So, but still you improve upon the accuracy. Now, what is the correlation between truncation error and the size of the grid? Let us see. The next article is about that. Now, the effect of grid size, increment and order of truncation error. I am just giving you an example. They are not accurate one, right? Because you notice that truncation error does not depend only on the delta x square, delta y square and delta x cube, etc. There are coefficients also with them. Okay. So the truncation error is not totally dependent on delta x square. Okay. So let us take a case in which your increment is same, both cases. There are two different grids and the grid size is same, the cases. But in one case your formulation is of the order 1 in the second the formulation order is 2. Now what will happen? The error will be square. In first case it will be first power of the delta x. In the second case it will be the second power of delta x. So what will happen? Your error will go down 10 times. So the grid size remains same. Just by increasing the truncation error, order of truncation error, you can increase the accuracy. Your truncation error would reduce by 10 times. Okay. In other words, what you can do is you can keep the truncation error same, right? Then what will happen if there are two simulations, two formulations in which the truncation error is same? What will you have to do is, suppose in one case your grid size is 0.2 meter, in the second case you will have to make it 0.04, because in one case it is the first power in truncation error, in the second case is double power. So only if this is the ratio between the two, you will get error of the same order, because error is squaring up. So actually the number should be square root of that. So 0.04 का square root हो जाएगा 0.2. So you are actually increasing 5 times the size. That means in the first case your grid size will be 125 times more than the. So there are two ways by which you can keep the error same. Or you can say either you increase the grid size, that means you increase the number of cell, reduce the size of the cell, you can reduce the truncation error, or you go to the higher order of formulation. So the people actually decide between them what to do. That should we go for a higher order to formulation, or we should go for a smaller grid, smaller size of the grid cell. Right? And you can see the difference between you are keeping the if you are keeping the or error size same, one grid is 125 times more than the other, because we are assuming 3D problem. Similarly, if your size is 0.1 meter in this case, the other case is 0.01 meter, right? So in one case the grid size, number of cells will become 1000 times, right? So when you make formulation of the order of 2, or let us say 3, you have to do more calculations. In other case you have to do more calculation because there are more number of cells. One has to trade off in between. So we will not be doing anything on that, we just know that this happens. Now the people who write the program, who solve the problems, they think about this, that which formulation they should prefer, and especially when they are at the limit. Because if you are not at the limit, your time constraints are not there, computer constraints are not there, you can take any formulation, right? Of course there would be other considerations also, but at least these considerations you can bypass, timing and size. But when you are at the boundary, you have to take care of them, right? Now this I was talking about in the beginning, that this is the actual term of truncation error, right? Even when one is a truncation order of 2, the other is truncation order of 1, you can't really compare them, because these terms are different. We were comparing the powers, but there are coefficients also. Not only that, the units of these two are also different, because when you take delta y on one side, other side it is delta y square, the coefficient would become 1 power less in distance. What will be the effect of that? That will also come in, because so it's not exactly, I just gave you some idea, and all these challenges people have to see that what is actually happening. I think we will stop here, except that I'll just tell you that the next topic what we are going to do. Now what we have done so far is, again we will start from the beginning so that we know where we stand. We started with the governing equations, which were describing the physics of the flow. Then we came to the turbulent flow, where we found that turbulent flow, we cannot solve those equations, because if we want to capture the turbulent flow, the grid size has to be too small. So we devised a technique which is called RANS, Reynolds Average Navier-Stokes equation. Okay, but when we do that, we find that there are 12 variables which are introduced, which depends upon the fluctuation which is happening in the flow. Turbulent flow is fluctuating flow. It's a random on an average. So there is the underlying average flow, there is a randomness at the top of it. Now that randomness leads to certain unknown variables, and we found that we took up one case of two equation model, where with help of certain assumptions, some sensible assumptions, scientific assumptions, we reduced those 12 variables to 2, and then we introduced two equations to solve those variables. So this was our formulation part. Now we have to solve them. So these differential equation, what we did, we saw that how do we break them into algebraic form. So we took first derivative, second derivative, mixed derivative, and broke them, and then talked about the boundary points at the boundary also. Now what we are going to do, we are going to discretize the equation. Earlier we discretized the derivatives. Now we are discretizing the equation. Once we discretize the equation, we have algebraic equation before us which we have to solve. So that technique is second part. So what we are next topic is that how to discretize the equation. So I'll just show you that how does it look like. Now you look at this equation. This is a familiar equation. It is unsteady, one-dimensional heat conduction equation. The simplest equation we have taken. Now if you look at this on the left side, it is first derivative. On the right side, it is the second derivative. What we do, we break it into algebraic equation on the left side and both on the right side. Obviously we will get some algebraic terms and the terms which are remainder terms, which are truncation, which are higher order terms, and we will put them separately, and those terms are ignored. Again we get an equation. So let me show. You can look at this equation. This was our partial differential equation. We converted this to an equation, algebraic equation, and these are the terms which we are going to leave. They are called truncation error. Same technique we are following. So now you can see that this how a differential equation is transferred into algebraic equation. This exercise we will do, and there are certain issues involved in this. We will talk about them. So we will stop here, and next class we will take up them.